In the previous sections, we introduced several important descriptive measures that are useful for transforming data into meaningful information. Two of the most important of these measures are the mean and the standard deviation. In this section, we discuss several statistical tools that combine these two. The standard deviation measures the variation in a set of data. For decision makers, the standard deviation indicates how spread out the distribution is. For distributions having the same mean, the distribution with the largest standard deviation has the greatest relative spread. When two or more distributions have different means, the relative spread cannot be determined by merely comparing standard deviation. In this case, we use the coefficient of variation. The coefficient of variation is simply the ratio of the standard deviation to the mean, expressed as a percentage. Coefficient of variation is used to measure variation relative to the mean. When the coefficients of variation for two or more distributions are compared, the distribution with the largest CV is said to have the greatest relative spread. For the population CV, we divide sigma by mu and multiply by 100%. For the sample CV, we simply divide the standard deviation by x bar and multiply by 100%. In finance, the CV measures the relative risk of a stock portfolio. Assume portfolio A has a collection of stocks that average 12% return with a standard deviation of 3%, and a portfolio B has an average return of 6% with a standard deviation of 2%. We can compute the CV values by dividing the standard deviation by the mean and multiplying by 100%. Here we see that even though portfolio B has a lower standard deviation, it would be considered more risky than portfolio A because portfolio B's coefficient of variation is 33% and A's coefficient of variation is 25%. We could also have a case where the standard deviation is the same, but the average stock price for a given portfolio is different. In this case, stock B is less variable relative to its price than stock A. Go ahead and open Excel airfare and determine the relative variability for the two flights. Begin by determining the mean and the standard deviation for each of the flights. In this instance, I will use the descriptive statistics output to make this quicker. Go into Data, Data Analysis, Descriptive Statistics. The input range will be the first flight. Be sure to check Summary Statistics, and we'll put the output range in the same sheet. Do the same thing again for the next flight. Now we can compute the coefficient of variation for both flights by simply dividing the standard deviation by the mean. As you can see, the Los Angeles to Salt Lake City flight has a larger relative dispersion than the flight from Los Angeles to Barcelona. Now that we've covered the mean, standard deviation, and distribution of data, we need to cover the empirical rule. Thinking of the standard deviation as a measure of distance from the mean, we can make assumptions if the distribution is nearly symmetrical and is approximately bell-shaped. Plus or minus one standard deviation from the mean contains approximately 68% of values. Two standard deviations contains approximately 95% of the values, and 3 standard deviation contains virtually all the data values. The empirical rule applies when a distribution is bell-shaped, but what about the many situations in which the distribution is skewed or not bell-shaped? In these cases, we can use Chebyshev's theorem. Chebyshev's theorem is conservative. It tells us nothing about the data within one standard deviation of the mean, but it indicates that at least 75% of the data will fall within 2 standard deviations. It could be more. If we apply Chebyshev's theorem to the bell-shaped distributions, the percentage estimates are very low. The thing to remember is that Chebyshev's theorem applies to any distribution, which gives it great flexibility. We will wrap up this discussion with standardizing data values. When you're dealing with quantitative data, you sometimes want to convert the measures to a form called standardized data values. This is especially useful when we wish to compare data from 2 or more distributions when the data scales for the 2 distributions are substantially different. To compute a z-score, take the difference of the data value of interest and the mean and divide that by the standard deviation. Be careful to watch out for the difference between a population and a sample. Let's finish with an example of standardization. Open up Excel file Country Growth and standardize the growth rates for each country. Begin by finding the mean and the standard deviation for the data values. To standardize the data, we can use a standardized function to find the z-score. Type equals standardize, select your x value, select the mean, pressing F4 will fix those values, comma, standard deviation, again F4, close parentheses, and press enter. Notice that the dollar signs will fix these values to an absolute cell reference and not change when we drag the cells down. Likewise, we could also use the standard z-score equation, where we take the x value minus the mean divided by the standard deviation. Either method works. To more easily determine which values are above or below 2 standard deviations from the mean, I'm going to sort largest to smallest. To do this, I'm going to need to insert a row and sort largest to smallest. As you can see, there are 6 countries with values greater than 2 standard deviations above the mean. If we scroll to the bottom, there are 2 countries more than 2 standard deviations below the mean growth rate. Thanks for tuning in. That finishes Chapter 3 in our discussion on descriptive statistics. See you in class.